I'm going to be talking to you about Hardy Weinberg equilibriums in butterflies, which is basically just an equilibrium that a population is in until something disrupts it. Here we have our population of butterflies. The three different colors have three different genotypes and different numbers in the population, blue, pink, and yellow. To prove Hardy Weinberg equilibrium, we have to calculate the frequency of each allele, so A and B. And that's going to be about 46% A, 54% B. Notice P and Q are equal to A and B. Next, we calculate the genotype frequency, and so highlighted in yellow are the frequencies of each genotype within the population. Notice that under the frequencies in the first column, I have the equations you can use to do that. Now we perform our chi-square test. We take our observed and expected. You get this total number down at the bottom of the chart, and you compare that to your degrees of freedom, which is number of genotypes minus number of alleles, and you compare those, and if they're within 5%, you do have a Hardy Weinberg equilibrium, so we do. Now we're going to add selection into the mix. We're going to talk about disruptive selection, and you can see that each genotype has a fitness. And this fitness level correlates with how well it is able to survive. AA has 1, which means that it can survive, it doesn't have any obstacles in reproducing, and AB and BB have obstacles, and the lower it gets, the lower chance of survivability. And you can see in the graphs, on the left, that's before this selection, and you have a higher population of AB genotypes, and then after we're going to have a lower population of AB genotypes, and I'll show you how this is possible. Here's our population of butterflies, and let's say that butterflies use flowers to camouflage themselves from predators. Here are our flowers with coordinating colors to the butterflies. So here they are. Let's say a disease comes in and kills some of the yellow flowers. It also kills more of the pink flowers. These butterflies now have no way to hide themselves and get eaten by predators before they have the chance to reproduce. Now you can see a different distribution of different colored butterflies. Here's the mathematical way to show this type of frequency after selection and taking fitness into account. And we'll get these frequencies after the selection, and you'll see a higher distribution of AA, a lower distribution of AB, and a higher distribution of BB, getting that distribution chart we showed earlier. After time, however, AB will not disappear from the population as one might expect because it has a lower fitness, because AA genotypes and BB genotypes will always be in the population, and there's always a chance of having an AB offspring with that. They just have a lower chance of survival.